Welcome to another exciting tutorial on our YouTube channel. Today we are deeping dive into the fascinating world of electrical engineering to explore two crucial concepts: maximum power transfer and Delta-Wye conversion. These concepts are fundamental for understanding how to optimize electrical circuits and ensure efficient power utilization. Whether you are a student looking to ace your electrical engineering exams or you are curious to unravel the mysteries of electricity, this tutorial is your gateway to mastering these essential concepts. So grab your notepad and let's embark on this electrifying journey together. In our last tutorials, we talked about Thevenin's theorem and the Norton's theorem. That is how we can replace a large circuit with just a voltage source in series with a resistor or a current source in parallel with a resistor. And our load resistor will be receiving the same amount of power. That is, there will be a power transferred from the large circuit to the load resistor and from the reduced Thevenin or Norton's equivalent circuit to the load resistor. In this tutorial, we want to talk about a theorem that introduces the maximum power. Like, how do we get the maximum power transferred to a load resistor? So for a practical voltage source that is shown in this diagram, this is a practical voltage source. Like I always say, that a practical voltage source usually have an internal resistance, and that's the essence of the Thevenin and the Norton's equivalent circuit. So this is a voltage source, right? So, and the voltage source for a practical one, that is the one you see physically, it has an internal resistance, and that's usually we call the Thevenin equivalent resistance, right? So this is a practical source, right? A practical source, and it has a load resistor is connected to it. So we want to see the maximum transferred to the load resistor, right? So what is power? Power is current times voltage, right? So I want to get the maximum transfer to the load. So the power transfer to the load is equal to the current flowing through the load multiplied by the potential difference at the terminals of the resistor, that is the voltage drop on the load. So how do we get IL? IL is gotten using Ohm's law. That is, IL is equals to Vs over Rs plus RL. So if you put it back into the power equation, then the power equation PL will be equals to Vs over Rs plus RL multiplied by VL. And according to Ohm's law, VL is equals to IL multiplied by RL. That's Ohm's law. So if I should put that here, right, so I'll be having Vs over Rs plus RL squared, because I have another IL here. So that is, this becomes IL squared RL, then multiplied by RL. So this is the value, or this is the equation representing the power delivered to the load. So to find the value of RL that will absorb maximum power from a given practical source, we differentiate with respect to RL. In engineering mathematics, we call something critical points. That is, if you have an equation, you want to get the critical points. That is, you want to get the maximum point, the minimum point, or a point of inflection. So what do you use to do? What we used to do is we differentiate with respect to that particular value. Let's say x. We differentiate with respect to x, and we equate it to 0, because at critical points the gradient is 0. That is, when you have the equation of a curve, y is equals to ax squared plus bx plus c, right? The point at the critical point of this curve will be at the point where the gradient is dy dx equals to 0. So, and that's what we'll be doing here too. PL is equals to this, right? So we want to know the value of RL that will give us the maximum PL, and the maximum PL, of course, is the critical point on the PL curve. That is on the curve showing the PL against RL. So we differentiate PL with respect to RL. So what would that give us? So the PL, the RL is equals to what? So we use the quotient rule. The quotient rule. Using quotient rule, what do we have? Quotient rule states that we have V du right, plus minus u dv minus u dv over v squared. So that is the quotient rule. So if you do that, v is our denominator, u is the numerator, and if you calculate that, we should have rs plus rl squared, because that's our denominator, which is v. Then if you differentiate the numerator, right, the numerator is vs squared rl, this is u, and denominator is what? The denominator is rs plus rl squared. So which means that du will be equals to what? It's equals to vs squared drl, right? And dv will be equals to what? If you differentiate with respect to side, we have 2 into brackets rs plus rl drl. So basically we have v du drl minus u dv drl over v squared. So if you input that here, we have rs plus rl squared multiplied by vs squared minus vs squared rl, that's u, then multiplied by 2 rs plus rl, then divided by v squared. V squared is what? rs plus rl, because it has squared before, so it will be raised to power 4. So these are the pl drl, right? So from here, what do? We equate the pl drl to equals to 0. That is, the pl drl should be equals to 0. So if that is equals to 0, so what do we have? It will remain only the numerator. So what do we have? We have rs plus rl squared vs squared minus vs squared rl. That is, we can bring the 2 forward, then multiply by rs plus rl equals 0. So if you factorize vs, if you divide through by vs squared, what do we have? That is, vs squared here, divide through by vs squared here, 0 over vs squared is still 0. So we have rs plus rl squared minus 2rl into bracket rs plus rl equals 0. If we divide through by rs plus rl, rs plus rl, rs plus rl, rs plus rl. So what do we have? We have rs plus rl minus 2rl equals 0. So which means that rs minus rl equals 0, which means that rs must be equals to rl. So what does that mean? It means that at maximum power, that is, if maximum power is to be transferred to the load resistor, the internal resistance of the practical source must be equals to the load resistor. That is, you have to put a resistance, you have to put a resistor that has a resistance equals to the internal resistance of the practical source. So in terms of Thevenin, we say that the load resistor must be equals to the Thevenin's equivalent resistance for maximum power to be transferred to RL. So what will now be the value of the maximum power? So to state this literally, that is, for us to know what maximum power transfer theorem states, it states that an independent voltage source in series with a resistance or an independent current source in parallel with a resistance delivers maximum power to a load resistance such that the load resistance is equals to the equivalent resistance. So let me use the values we use there, that is the naming convention we use there. An independent voltage source in series with a resistor Rs, or an independent current source in parallel with a resistance Rs, delivers maximum power to a load resistance RL right, such that RL is equals to RS, such that RL is equals to RS. An alternative way to view the maximum power transfer is possible in terms of the Thevenin equivalent resistance of a network. A network delivers maximum power to a load resistance RL when RL is equals to the Thevenin equivalent resistance of the network. That's just very, very simple. A network delivers maximum power to a load resistance RL when RL is equals to the Thevenin equivalent resistance of the network. So like I was saying, that this RS in terms of Thevenin, it's same thing as the Thevenin equivalent resistance. I hope that you understand what I've explained so far. So this means that the maximum power transfer tells us that a 2 ohm resistor draws the greatest power, that is 4.5 watts, from either practical source when a resistance of 0.01 receives maximum. I want you to know that there is a distinct difference between drawing maximum power from a source and delivering maximum power to a load. They are different. If the load is sized such that its Thevenin equivalent resistance is equal to the Thevenin resistance of the network to which it is connected, it will receive maximum power from that network. Listen to me again. If the load is sized such that its Thevenin resistance is equal to the Thevenin resistance of the network to which it is connected, it will receive maximum power from that network. Any change to the load resistance will reduce the power delivered to the load. However, consider just the Thevenin equivalent of the network itself. We draw maximum possible power from the voltage source by drawing the maximum possible current, which is achieved by shorting the network terminals. In this extreme example, we deliver zero power to the load. A short circuit in this case, that is P is equals to I squared R. We just set R is equals to 0 by shorting the network terminals. I explained to you in our previous terminal that if you are shorting a terminal, it means that the resistance there is 0. But if you are opening a terminal, it means that the resistance there is infinity. Current cannot move. The resistance there is infinity. So let's apply a bit of algebra to get the maximum power transferred. So from our previous equation of the power transferred, we have PL is equals to Vs squared RL over Rs plus RL. Alright, Rs plus RL squared. So now, because RL is equals to Rs, so let's replace Rs with RL. So PL will now be equals to Vs squared RL over RL plus RL squared. So what does that mean? I have Vs squared RL over 2RL squared. So therefore the PL, the power delivered to the load, will be equals to what? Vs squared RL over 4RL squared. That means that the power delivered to the load is Vs squared over 4RL. In terms of Thevenin's theorem, we say that VTH squared over 4RTH. That is the power delivered to the load. So let's take an example. This is the example we'll be using to explain the maximum power transfer. So don't be scared, it's just a very, very simple question. The circuit shown is a model for the common emitter bipolar junction transistor amplifier. Choose a load resistance so that the maximum power is transferred to it from the amplifier, and calculate the actual power absorbed. Since it is a load resistance we are asked to determine, the maximum power transfer theorem applies. The first step is to find the Thevenin equivalent of the rest of the circuit. That is, this is the load resistance, right? So the rest of the circuit, let's get the Thevenin equivalent circuit. So how do we get that? We want to get the resistance, right, and also the voltage source. So what do? We'll draw the circuit removing this RL, right? So the first thing is to do is let's calculate the Thevenin equivalent resistance. And how do we do that? We turn off all independent sources. So when we turn off all independent sources, this is a voltage source, right? When we turn it off, it will become a short circuit. So what do we have? We now have 300 ohms, right, in parallel with 17 kilo ohms, right? Then in parallel with 5 kilo ohms. Then this, because this is a dependent source, so we are not shorting it off. So if you go back to our Thevenin and Norton theorem, you discover that I told you that we are not turning off dependent sources. So we don't turn off dependent sources. So we have 1 kilo ohm here, right? So we have this thing here. Then I'm looking for the RTH. But look at something. This is V pi, right? And this is 0.03 V pi. So if you have to get the value of V pi here, this dependent source is depending on V pi. So what will be the value of V pi here? There's no source on this other side. In bipolar junction transistor, we call this side the base side, right? And from here, you can see that there's no source. Actually, from a base, there should be a source for the transistor to start working. For the transistor to start working, the base must be biased. That is, there must be a source that is powering the transistor, right? So the source has been short off here, which means that there's no power getting to this resistor, this 5 kilo ohm resistor. So therefore, V pi is equals to 0. And if V pi is equals to 0, it means that this dependent current source is also equals to 0. So if it is equals to 0, it means that there is an open circuit at this side. There is an open circuit. So which means that what will RTH be? RTH should just be the value of this resistor, right? Because this resistor here is not connected to these other ones. They is neither in series nor in parallel to this other one. So the RTH from this side, from the load side, is what? 1 kilo ohm. Therefore, RTH is equals to 1 kilo ohm. So we've gotten our Thevenin equivalent resistance. So let's get the Thevenin equivalent voltage. So if you look at this, that is, if you cut this out, right, we want to get the Thevenin equivalent voltage, right? So plus minus VTH. So if you are looking at the circuit, this network on this left hand side from the right, so what do we see? We only see this and this. This is usually called the collector side for a bipolar junction transistor, right? So you only see this and this. This is the emitter, right? It's usually grounded. This is the base, and this is the collector. So that's why it's called a common emitter bipolar junction transistor, right? Both of it has a common emitter, right? So VTH is only composed of these two devices. It's only composed of these two components, the current source and the resistor. So if you have to get VTH is equals to what? It will be minus 0.03 V pi, right? It is going down. The current is going down. So that's why it is negative, right? Because if it is going up, it will be positive. The positive is here. The negative is here. So if the current is coming like this, it will enter to the negative, right? Then multiplied by 1 kilo ohm, right? So that is 30 minus 30 V pi. So that is our Thevenin equivalent voltage. But how do we get V pi? That's very simple. That's very, very simple. We use the concept of voltage division. Look at it here. This is a voltage source. This is 300 ohms. And this is the V pi we are looking for, right? So this V pi is the same voltage on 17 kilo ohms. Why? Because they are in parallel. Devices in parallel, components in parallel have the same voltage, right? So because they are in parallel, they have the same voltage. So I can combine these two and use them to get V pi, and use it to get V pi by applying voltage division. So if I do that, the resistance combination of 17 and 5 kilo ohm will be what? So we have RT will be that 17 times 5 over 17 plus 5. So that will be giving us what? This will be 22 and this will be 85. So this should be giving 3.864 kilo ohms. So therefore, which means that I'll now be having 300 ohms, right? The equivalent resistance, then the voltage source. This is sinusoidal voltage source. It's an AC source, right? Because when you see this, you already see the sinusoidal sign there. So which is 2.5 sine 440 t millivolts. This is 300 ohms. And this is 3864. And of course, I'm looking for V pi. So by voltage division, V pi will be what? 3864 over 300 plus 3864. That's voltage division, multiplied by the source, which is what? 2.5 sine 440 t millivolts. So if we calculate that, this is our V pi, right? So we remember that our VTH what is our VTH? VTH is equals to minus 30 V pi. So minus 30 V pi. So if you multiply minus 30 with this V pi here, you'll be having minus 69.6 sine 440 t millivolts. So therefore, we can now get the maximum power. So the maximum power will be given by VTH squared over 4RTH. Remember how we got this. So if you divide that, that is minus 69.6 sine 440 t, of course milli, that's times 10 to the minus 3, everything squared, over 4 times 1000. So the maximum power transfer, P max, equals to 1.211 sine squared 440 t microwatts. Micro means 10 raised to the power minus 6 microwatts. So that's the maximum power transferred to the load. That's very, very simple. If you have any question on maximum power transfer, please drop a comment on the tutorial and I'll make sure I give you an answer. So the last topic I'll be touching in this anti-circuit analysis is Delta-Wye conversion. This is related to resistances. That is, we saw previously that identifying parallel and series combination of resistors can often lead to a significant reduction in the complexity of a circuit. In situations where such combinations do not exist, we can often make use of such transformation to enable such simplifications. Consider the circuit drawn. You can notice that there are no series or parallel combinations that can be made to further simplify any of these circuits, right? And if you notice that this one and this one, they are the same, right? I explained the concept of single node pair circuit in our previous tutorial, right? That is, this node here and this node, they are the same, so I can combine it to just form one. Whether I combine it or I do not combine it, they are the same node. So these two, they are the same. I just had to draw it in case you see something like this. None of them is in series. This and this, they are, it's, for example, they'll be connected to other components, right? So you cannot say this and this are in series and this and this are in series, right? So the three of them are not in series, right? And these three too, they are not in series. They are not in series. They are not in parallel. So you cannot make any reasonable conclusion that they are in series or in parallel. These two same thing, you cannot make any reasonable conclusion that they are in series or they are in parallel. So that's where the concept of Delta-Wye conversion comes into place. So basically, there are proofs that can prove this. I can prove this for you, but I won't do that in order to cut short this video, right? So I'll write the equations that can be used to convert delta to y or y to delta, so that one can simplify based on the network we are given. So imagine we have given a very big network of resistors, right? Where you discover that there's a particular delta connection between three resistors, and if you can see that if you connect it to y, it will make maybe R1. It will make maybe R1 series to another adjacent resistor, or making R1 or making R2 parallel to another resistor, so that it can simplify your circuit. So that's the purpose of Delta-Wye conversion. So these are the equations. These equations are very easily gotten from the circuit, right? It's very, you don't need to cram them. They are very easy to get, right? And I will explain how you can get these equations from the circuit without even proving. So it's very simple. Y to delta, that is, if you are converting from y to delta, sometimes it's usually called star, right? Because it looks like a star, right? This like this, right? It looks like a star. So sometimes, maybe in some textbooks, you see star to delta or delta to star conversion, right? Star delta conversion, delta star conversion, right? So look at it. They are very easy to get. Y to delta, they have similar equations: R1 R2 plus R2 R3 plus R3 R1. Just like the three resistors that are forming the star, right? You multiply two of them together and add them together. R1 is multiplying R2, R12 will multiply R3, R2 will multiply R3, right? This is it. Then divided by R2. Let me now explain how this denominator is gotten. You can see that the numerator, they are the same, right? This, they are the same. Let me now explain how this is gotten. Star to delta. So this is star, right? And you want to get delta, right? So this is RA. So I will draw the delta here. This is R3, right? This is RA, and this is RC. This is RC, this is RA, and this is RB. So to get RA, of course, the numerator is R1 multiplied by R2, R1 multiplied by R3, plus R2 multiplied by R3. But the denominator will be R2. So how do I get that? When you draw your star, you want to convert it to delta. So draw your delta on top of the star, right? So the resistor that is opposite to the resistance you are looking for RA. Which resistor is opposite to it? R2. That will be your denominator. So RA will be what? R1 R2 plus R1 R3 plus R2 R3 divided by R2. What will be RB? RB will be divided by what? R3. That is, RB will be equals to R1 R2 plus R2 R3 plus R3 R1 divided by R3. And what will be RC? RC will have the sum of R1 R2 and R3 divided by R1, because R1 is opposite to RC. So it's just like you want to do the sine rule. Remember how the sine rule is done. So sine rule will state that sine A over A, that is, if you have a triangle, right? This is A, this angle A, this is angle C, this is angle B, right? And this is A, B, C. We will say that sine A over A divided by sine B over B divided, because B is opposite to this side is opposite to the angle. So it's just like as if you are doing sine's rule. Do you understand? So for delta to y, that one too is very, very simple. So you draw your star inside the delta. So star to delta is that you draw delta outside, so that you now find what the resistor opposite to what you are looking for. And of course you do R1 R2 plus R2 R3 plus R3 R1, then divide by R2. But for delta to star, you draw the star inside, right? So you have your star here, this one here, and this one here, right? So this is R1, this is R2, and this is R3. So for delta to star, the denominator is the same. The denominator is usually R1 plus R2 plus R3, RA plus RB plus RC, right? Because the delta resistance are labeled RA, RB, and RC, right? So the denominator is the same, RA plus RB plus RC, RA. But how do we get the numerator? So that too is very, very simple. Delta to star. So this is R1, right? The resistors that are adjacent to R1, that will be your numerator. R1 has what? So if I want to get R1, right, for a star, it will be what? RA multiplied by RB divided by RA plus RB plus RC. What will be R2? R2, the two resistors that are adjacent to it is what? RB and RC. So it will be RB multiplied by RC over RA plus RB plus RC. So if I want to get R3, what will I do? The resistors adjacent to it are RA and RC. So it will be RA multiplied by RC divided by RA plus RB plus RC. That is very, very simple. So you can see, you don't need to cram it, you just need to know how to do it. For star to delta or y to delta, what do? The resistors opposite the resistor you are looking for. But for delta to y, you will multiply the resistors adjacent to it. And notice that for y to delta, the numerator is the same for all the resistors, and for delta to y, the denominator is the same. And that's just simple, very simple. So you can use this to simplify any circuit you want. So let's do an example. So this is an example to illustrate delta to star or star to delta conversion. So this is very fancy. We want to get the equivalent resistance of this network. So what do? You can see that there's no way you can see that a resistor is in series with another resistor. So no, it is not possible. Well, because these ones, they are connected to another component, right? So you cannot say that they are in series or they are in parallel or they are no. It doesn't work that way. So you can see at the top is in delta shape, and the bottom too is in delta shape. So you have to choose which one you want to which one do you want to convert first. You can convert delta, you can convert the bottom delta, and you can convert the top delta. So what I will do is to convert the top delta, right? So all I do, I will draw a resistor here, I want to convert it to star, and draw another resistor here, right? So let me call this R1, R2. You see that I won't be checking any formula before I can get this. I'll call this R3. So what to be my R1? It is delta to star. So R1 will be what? Adjacent resistors, which is what? 1 times 3 divided by the sum, that is 1 plus 3 plus 4. What is R2? R2 will be 1 times 4 over 1 plus 3 plus 4. And R3 will be what? R3 will be 4 times 3 over 1 plus 3 plus 4. That's straightforward because 4 and 3, they are adjacent to R3. So this will give us 3 over 8. This will give us 4 over 8, that is 1 over 2. And this will give us 12 over 8, which is what? 3 over 2 ohms. Right? So if I redraw the circuit, what will I have? I will have 1 over 2 here. This is R2. I have 3 over 8 here. then 2 ohms, then 5 ohms, then 3/2, right? So this is 1/2 ohms, this is 3/2, and this is 3/8 ohms, right? This is 2 ohms, this is 5 ohms. So now you can now see that these two resistors now, they are in series. These two resistors too, they are in series, so you can now combine them together. So and the combination of these two now be in parallel. So let us do that. That's, we have 1/2 ohms here. So when we combine these two in series, what do we have? We have 2 plus 3/8, that is 19/8, right? So and these two will give me, that's 5 plus 3/2, that is 6.5, which is 13/2. So I have 13/2 here, 13/2 ohms, and this is 19/8 ohms, and this is 1/2, right? So these two are in parallel, right? Because they are in parallel, you combine them together and they are in series with this. So if you do that, that's 1/2 plus 19/8 parallel 13/2. I already taught you how to combine resistors in parallel. If you don't understand that, go to our first tutorial, you see how to combine resistors in parallel. So the result of this will give us 159/71 ohms. So you can see how we resolved this whole network into just one resistor, and the resistor is 159/71 ohms, and that's it. Delta-Wye conversion. So this is the end of our tutorial today. If you have any question on what I've taught so far, please drop a comment under this resistor, like this video, and make sure you share to others so that they can learn what you've learned. Thank you very much, and see you in the next video.